speak up top with no audience. That's kind of boring. Can't tell whether your text is too small until after it's over, and you don't know if you're being heard or not. All right. Well, good afternoon. I'm here again. Today's lesson was about checksums, unless people have questions that distract me from that purpose. And the idea behind a checksum is to generate some relatively small value that you can use to pretty much verify that some data has been copied successfully. So you can download an ISO image, and those usually have an MD5 sum value associated with them, which is a fairly large string of bits. And if you see the same MD5 value, then you probably have the same value. The idea behind a checksum is to generate some relatively small value that you can use. Holy crap! To pretty much verify that some data has been copied successfully. So you can download an ISO image and look. What the heck's going on?
My guess is somebody. Well, I mean, I'm the only person on the stream right now. I would say somebody has their mic open and you're getting a repeat lag, but
it's just me and you.
Yeah, and I'm muted.
Long lag.
Yeah, it was.
I hope it doesn't continue. All right. I started on a checksum program, which I'm going to switch to, and I'm going to change the way EB appears so that the dock widgets are separated, and that will make it clumsy switching around, but easier to make a fairly nice size for the windows. So I'm doing that now. The unfortunate thing is this program wants to put all the dock widgets on top of the main window, and I have to get them out of the way in order to have them visible simultaneously. All right. Screen share. Is that moderately small?
Yeah, it's awfully small.
All right.
Oh, that's much better once I full screen my my window.
What the heck am I doing with a... I was playing with some stuff that doesn't make any sense. All right. So what I've got, in addition to trying to do checksum, I was experimenting with seeing how big I could make the array and have an array work properly. Checksum there. All right. So I've got a BSS segment, and as you can see, it's 10 gigabytes. This seems to work, though I haven't checked a 10 gigabyte file. And if I give it the name of a file and tell it to run the program, the computer has gotten confused. Line 4, an instruction expected after a label. I was trying to see if I could sneak line numbers in because I've got troubles with translating line numbers in Windows, experimenting with macros. All right, so now we're here, and this is where I'm checking to see if the first parameter is greater than 1. If it's greater than 1, then I have a file name on the command line, and I do. And now we're going to move the name in there, call the open function, and move. Let's see, we got register somewhere. Maybe I don't. May have killed the registers. I'll see if I can move the register window to make it visible. Yes. That's one convenient thing. I can move it in and out. So I got number 5 for the file descriptor, and I've got other things going on. Normally your next file would be a 3. But if I then go down and get ready to read, put the file descriptor in register RDI or EDI, which is good enough, and then the address of data into RSI, and then I tell it to read 10 gigabytes. And if I drag my register window back into visibility, we can see that the read function has returned 74F, which I can change to decimal 1871. And I should be able to call one read and read most files I would like to compute checksums for. All right. So the question now is, how do we generate a checksum function? I'm going to start with a checksum function I'm making up. Move that toolbar out of the way. I don't use it anyway. I can tell it to quit debugging. And what I'm going to do is to take the values and read them 8-byte quantities at a time, and then manipulate them so that I get the final value in some sense dependent on all of the bits of the input. If I were to do something kind of stupid like just take the values and add them, then it kind of maintains certain bits, like the low order bits will be more likely to be represented in the bit 0 of the result. But if I shift things around, I can get a mixing of values. And I think this may be close to the System 5 checksum. So if I want to do a checksum, then I need to have, I'm going to make a call to a checksum function, and I'm going to pass the array in there just because that's what I prefer to do. And then I want to move the size that I have read into RSI for the second parameter, and that's REX. And call checksum. Let's see how this works. So I'll tell it that, well, I don't have to make it glow in order to use it from here. I think I'll be fine just making a checksum function. And I kind of got in the habit of making the beginning of functions start on a line by themselves, and then I'm going to move RBP or push RBP and then move it like I normally do for a function. Now, here I have a question. Do I need any local variables? I don't know. I'm going to assume that probably it would be handy to have them, so I'll do a subtract sub RSP 32. I won't be calling any other functions, but it would be nice to handle this, to have the space for local variables if I need it. Now, the number of bytes that we've read is not too handy as is, because I want to work on it in quad words. So I'd like to put zeros after the number of bytes to fill out a whole number of quad words. So how many quad words is it? All right, we've got RD or RSI has the number of bytes and the number of quad words. Let's see, how do we translate a number that's not a multiple of 4 into not a multiple of 8 into a multiple of 8 that's rounded up? Well, the way I tend to do it is to add 7 and then divide. So if I do add RSI 7, that will, if it happens that it is 1 more than a multiple of 8, then it will become a multiple of 8. If it's 2 more, it'll be a little bit bigger than a multiple of 8. And if it's 7 more, it's going to be 6 more than a multiple of 8. So I won't be overdoing it. And I really want the number of quad words in this thing, so I think I will test this, and if I shift it right 3, it should be okay, and I'll finish off a function for now and see how it works. Leave return. All right, so I think it would be handy to get rid of that main checkpoint's gone, or breakpoint's gone, so let's start down here and see what we get. All right, we got 1871 for the number of bytes, and then if I step forward, add 7 to it, oh, excuse me, in RSI, it was 756 as a hexadecimal. As a decimal, it's 1878, and then if I shift it right 2, I get 234. And 234 times 8 is what? I'll check it with my handy computer here. I use the calc program, which is kind of handy. It was it 234 times 8? 1872. All right, so we started with 1871. We need to manage to fill it on out to 1872. But I don't want to have the thing be dependent on just whatever happens to be in this extra byte that I'm now going to use. I'd like to wipe out all the bytes from 1871 to 1872 with zeros. So let's do that. So before doing this stuff where I'm shifting and adding and shifting, how about if I save this value into a register? R8 is a pretty good register. Now I need to store bytes in the array. So I need a loop. And how many times will it execute? Maybe 0 times, so I need a test at the start of the loop. Using .loop, it will make it be a local label, so it's local inside checksum. And I want to compare, let's see, can I compare R8 and RSI? Excuse me. How about we shift it back left? All right. So if it's equal, then I would like to finish this. I think that means I've got them all done because RSI is the count of the number of them. The index needs to be one less. So how about jump greater than or equal to end dot loop end, and we'll test it to make sure it looks okay, and then we'll need to move a byte into about AL data. Data is now in a register RDI plus R8. And then, let's see, we don't want to extract that byte. We want to put a 0 into that location. I'm sorry. Byte. Now, it may be better to store the byte 0 into AL before, because if I use a 0 as part of the instruction, it's going to end up taking 32 bits for that value. And if I use AL, I don't need to put byte there. So how about we do XOR EAX comma EAX, which is probably about 2 bytes. And now I should be putting a 0 in there, and then I can increment R8 and jump to the top of the loop. Well, I have done enough. Let's try it and see what happens. And I'm going to slide my register window back into view. Move it down so I can click on that button. All right, so R8 has 1871, which I may as well convert to decimal. And then we get 1878, 234, and 1872. So compare, and we have the sign flag set. I think I'll turn off the tooltips. Have the sign flag set, which means the number is negative. R8 minus RSI gives a negative. That means R8's less than. So we move a 0 into RDI plus R8. R8, remember, is the size of the number of bytes that were read from the file. So adding that value to the beginning of the array should be the first byte that we want to 0. Increment, jump to the top of the loop, and now they're equal. So we go to loop end. All right. That preliminary is out of the way. Now we want to shift it right 3 to be the number of words or quad words to process. and we want to go through a loop and accumulate some bits. So let's just do some accumulation, and we can start. It's fairly common to start with a -1. So let's do, we've got EAX is a 0 right now, so we can subtract EAX 1. All right. I guess we can decrement. How about RAX? I want to work on all the bits. Decrement RAX. And now I need another loop. And how many of these are there going to be? I guess I could have a file that has 0 for the number of bytes in it. So I guess I'll put checksum loop. We'll again need a counter, and I think I'll use R8 again. R8D will give us the 32-bit thing, which takes one less byte. And now we want to extract a value from the array and put it in together with RAX, which is where we're going to accumulate the value. So we want to test to see if we've done them all. And RSI is the number of quad words, so we'll do a compare again. R8, RSI. And when we have an equal, then we have processed them all. Checksum. I keep typing the wrong characters. Those are not all that close on the keyboard. All right. So if we're still in the loop, we have another value to access, which I'm going to get with move. Move into, how about R9, and the array is RDI, and plus R8 will give us the index to use. And after we've moved it, we want to combine it with RAX. And I'm going to choose, I think is it rotate right, ROR? I believe it is. RAX, comma 1. And then, how about exclusive OR? RAX, R9. So I won't be throwing away values from the first part. I'll be accumulating it, but I'll be accumulating the first quad word with the second, shifted a little bit. That should be fairly interesting. To mix it up a little more, how about rotate right R9, 5 bits, and then exclusive OR one more time. And we want to add 4 to add 8 to R8 to process the next one, and then jump to the checksum loop. All right. Maybe this is right. Let's see how it behaves. Stepping through what we've done before. This is where we're putting 1 0 at the end of this array, which needed one more to make it a multiple of 8 bytes. to process. And now we're ready to shift right, and we have 234 quad words to process, and we use R8 as our index, so it's 0, jump greater than or equal, checksum end, and we're not going to do that. We'll move into R9. That looks pretty handy. So the first line of the file, this came from a listing file, has spaces and then a 1 for line 1, and then some more spaces and then some more stuff. So we seem to be processing the right data. All right, now we're ready to exclusive OR this, and since we're doing checksums, I'll change this to hexadecimal, and this gets to be an adventure. A rough spot in the program that I haven't gotten around to fixing yet. It's not showing us all of those bits. How about let's go one more step. All right. It is so annoying trying to get the cursor exactly in the right spot for resizing. I don't know why anybody would design resizing pieces of a GUI where they have to be exact. All right, let's put it down here. All right, so after we did this exclusive OR, you can see the 2020 stuff ends up with some bits that are pretty much repeated patterns of DF. And then the next thing is to rotate 9. Come on. All right, rotated, we get a different pattern. And then I've exclusive OR'd that with RAX. And then let's see what happens with the next thing. All right, so we go in here and get the next byte, our next quad word, which is all spaces. And if we rotate RAX, we get a strange looking pattern. And then we exclusive OR that. And then rotate and exclusive OR. So far, these values are leaving the number with a lot of repeated patterns. So eventually it's starting to become something that looks kind of random, which is what you get with checksums. Now, the reason they use exclusive ORs has something to do with some abstract algebra using group theory, where they are ending up effectively in some of these checksum algorithms, they're doing a division that doesn't require a lot of work. The division is essentially just an exclusive OR. And the reason they do that is because by using a mathematical basis for this, then they can conclude that things like if one bit changes, your checksum's definitely different. You don't lose anything, from doing something stupid like what I've done. Possibly you'd lose something early on in the file. Who knows? I can't be sure. And they can also say confidently things like, if 2 bits are changed and interchanged, then they'll also detect that kind of difference. So there are some conditions where various checksums work pretty well. And I want to change this thing now to use something a little more rational, and I'm going to go for my browser, if I find the browser. This will work. Google Hangouts. Oh, here we are. I think the BSD checksum is a fairly good one, and it's easy to implement. Let's see. Is this readable? I assume it probably is. All right, so let's examine what this checksum algorithm does. They have checksum equals checksum shifted right 1, or added to the checksum shifted left, checksum and 1 shifted left 15. That's a rotate. Which direction are they rotating it? They're rotating it to the right. They shift it right, and then they take the rightmost bit and put it on the left, and they're accumulating a 16-bit number. So the first thing they do is rotate the checksum, and they started it with a 0. And then they take a character and add it to the value that's there, and then they clip it. Well, if we're going to maintain a 64-bit number, let's try doing a similar thing, rotate it 1, and add in the next 8 bytes and see how this works. I'm doing screen share. I'd like to change it. All right. So what we wanted to do was to rotate the original value every time we enter the loop. And if we're going to do exactly the same thing, we don't really need to decrement to start. We can have REX as 0, and before we do anything with R8, R9, we can do a rotate right. And if all we're going to do is add it, there's not much reason why we would want to move it and then add it. We'll just do an add. This is probably going to be an OK algorithm. And it's shorter. And I will pick it up down here, get rid of the breakpoint on 17, and start it up. And we're doing approximately the same as the BSD checksum algorithm. All right, shift it right to give us a number of words to process. And I've got R8 is our index register, so we got that. And we're not through processing. Rotate right, RAX, well, it's 0. Add the first thing in there, we get the first 8 bytes identical. Then if we go into the next one, we rotate right, and we get 1010 everywhere. And then add in the next. And once again, with it being so much of the data is all spaces, 20 hex, then you don't see much variety for a while. All right, so rotate that right, and now we get a bunch of 1/8s and a few bits that are different. Add in the next piece, and this is, as far as I can see, somewhat similar to the original thing that I just made up. Now, BSD checksum is not a really robust checksum, but it probably works fine for a lot of cases. All right, after doing a bunch of them, we got R8 at 112. We've got enough of them done so that the pattern doesn't bear any kind of resemblance to having a bunch of spaces. And I will catch it here, tell it to continue. And at the end, we have 809952F563 6B33AC. All right, I will switch back now to the browser. Oh, that one. There are lots of checksum algorithms. Some of them are pretty straightforward. There's one that I documented in the book that is Adler 32, which is not too hard to understand. And I'm not going to do it because I left it as an example for an assignment for people to work on. All right. It's easier to see as just the code. Reading their description might drive a person crazy. And this one, the data is an unsigned character array, and they're processing a byte at a time. And then they do A equals A plus the data mod whatever mod Adler is, and then they have B equals B plus A mod Adler, and then at the end they shift it B left 16 and orient the A. So it's, I don't know what mod Adler is. The sums are done modulo 65, 521. And that's the largest prime, apparently smaller than 2 to the 16. So doing mod with a prime gives you some pretty unique looking patterns that are not very much connected with the other stuff. But this is doing an integer division to do mod. And if you look at some of these others, cyclic redundancy checks, I don't know if that's in here or not. How about Fletcher's checksum? And it says a position dependent checksum. It says to provide error detection properties approaching those of a cyclic redundancy check with lower computational requirements. So let's see what Fletcher 64 looks like. Well, maybe the code will be in here. All right, here's Fletcher 16, which will give a flavor of how this works. So you have two sums that you're working with, similar to the last thing we looked at with A and B. And you go through the data byte at a time. Sum 1 is sum 1 plus the data at that index. and they've got mod 255. And then sum2 is sum2 plus sum1 mod 255. This seems quite similar. There's a Fletcher 32 function, and with Fletcher 32, they're processing it words at a time, and they use a little advantage here in that it won't overflow a 32-bit integer. If you start with 16-bit numbers and you're adding them together like this does, just sum2 equals sum1 plus the data, and you increment the data. If you do this, you're not going to overflow, and it's guaranteed that you won't until you make it to 360 words or more. So these are just adds, and they've reduced the computational load considerably by doing just adds up for a while. And then after they've added up to 359 of them, they do this thing where they AND it with FF, and that gives you a 16-bit number. And then they add to that sum1. So sum1, they're taking the two halves of this number and they're putting them together. They're taking the right half, and then the left half, they shift it right 16 bits, add it to the other half. They do the same thing with sum2. Then at the end, they do this again with each of the partial sums to get two 16-bit numbers, and then they OR those together, taking sum2, shifting it, and let's see. I have done the Fletcher algorithm, but I have a hard time remembering what my code was. I may have done that under Windows. I can't remember. All right, this is time to switch computers. I think I've got a working thing under Windows. Let's just copy the thing from Windows to Linux. And I'm going to kill the EB program and start it up again, and then we'll switch to it. All right, ready to switch. So back to the Hangout. All right, so here we have some code, and this is two different functions or two different files. Fletcher.c is a main routine, and I'm not going to get rid of the Windows business in here, but to have a file which has assembly code and C code, you need a project file. And a project file is effectively, like we're seeing here, it just consists of a collection of names. I got Fletcher.c, Fletcher_ASM.asm, and those names are goofy, but I'm going to look at this part. When EB sees these names and it has a .ev file that it started with, it knows it's the project, and it will compile the .c file, assemble the .asm file, and build one program. All right. Yeehaw, that's a lot of crap. I've been tinkering with Windows, so I don't really want to run this thing, and it's not going to be very obvious how this works. All right. So I made a Fletcher 64, and it's doing the same sort of thing as the one before, and I haven't done the optimization where I'm trying to figure out how many things I can accumulate before I start overflowing, but I certainly didn't have any problem with 1,000 of them. I had a problem with 10,000, I think. So I did the same algorithm as before, but where they had 4 Fs, I made it 8 Fs. And where they shifted 16, I shifted 32. And this seemed to work pretty well. Let's see if I can get rid of the Windows garbage. Ooh, large integer. In order to do timing with Windows, I had to use large integers, and large integers have, it's a union, and a quad part is a 64-bit integer in that. So I'm just going to get rid of this timing stuff. All right, so we read some data and have a size that we're trying to read. And I did a similar thing here. K is n plus 7 divided by 8 times 8. And I do no more than size just to be sure. And this is calling the Fletcher file by itself. I think I will close the project. Let's just start over. Oh, I need to screen share. Get rid of some Windows stuff. Not going to be doing querying performance. All right. This is a C program, and let's see. I think I'll catch it in the Fletcher function. More Windows garbage. Windows has a long is a 32-bit integer. So I put long in a few places to make EB happy with it. And under oh, so data is unsigned int. So let's change that to unsigned int. It's got one of these pieces in it. With Windows, you have to worry about whether a file is binary or text. And the reason is if you're reading a file in Windows and you don't specify binary, anytime it encounters a carriage return followed by a new line, the read function will change it to just a new line character. So if you're trying to do a checksum, you're not going to get a checksum that would be the same as you would under a Unix computer. It also does a little goofy thing. If you try to read 100,000 bytes, you'll get 98,000 or something, depending on the number of lines. So it'll have fewer bytes than you've asked for. And let's see if this thing is ready. And we'll quit in a minute or two, but I would like to see Fletcher make it. I'm not sure which one of these has it in there, but probably it's one that I haven't included. But standard lib. The text in EB is easy to see the difference between unused variable. And it's easy to see the difference between periods and commas. I think I'm down to one error. Long F1. Oh, it says it's set but not used. So perhaps if I would do a print, I would be making some real use for it. All right, now we're going to go through the loop and see how this behaves. So we figure out some number of words to work on, and if I view the data, I should be able to observe things readily here. So we have TLEN, temporary length, and we have that set to -1. That doesn't make sense. think this file doesn't exist. How about we try a different file? memory.asm. So let's run it again. And down here we see words is 147. TLIN 147. So then it does sum2 plus equals sum, which is plus equals data, and the values get accumulated. This changes pretty rapidly. And so at this point, they're pretty dramatically different. And it processes a bunch of them with just essentially adds and subtract instructions to get the job done. And at the end, we have these values, and you shrink them down to 32 bits with that combination stuff. Let's see if I'm going, I may have restarted. No, there we are. All right, so it says return sum2 shifted left 32 ordered with sum1. So we get that value, and we get Fletcher equals, and use the terminal. You get a 64-bit checksum value, which should be printed in hexadecimal. All right, it's hexadecimal. It makes a nice number, very fast. It has a lot of mixing going on. I don't have time enough to adjust the Fletcher algorithm to be an assembly under Linux, but I think we know enough about checksums that we could do it. Maybe another time. I think this is enough for today. Bye.